A function is basically just any graph that you can plot, okay? So all of the graphs that you have learned in grade 9, including the linear and the parabola, the quadratic, okay, these ones are all considered to be functions. Okay, and pretty much any graph that you can draw in grade 10, you should also have learned the circle. Okay, like x squared plus y squared equals r squared. These are all going to be defined as a relation. Everything is a relation. Okay, as long as you can relate one variable to another, it's a relation. Okay, but in grade 11 and 12, they mainly focus on functions. And the thing that separates functions and relations is that functions basically indicate for every single independent variable, you should only have one corresponding dependent value. Okay, so what that means is for every single x value, you should only have one y value. So if this is 1, then ideally you only have one corresponding y value. So all of these are considered to be functions. These are all functions. Okay, but if you take a look at the circle over here, if we look at when x equals to 2, your y can actually be two possible values. One positive value. You can also have a negative value right here for your y. So in this particular case, this is not a function.
So I did learn about this a little bit in my grade 10 AP class.
Oh, perfect.
Like the perpendicular line rule and stuff. Or no,
Oh, yeah, the vertical line.
Yeah.
Yeah, exactly. So basically, this is known as the vertical line test. And to put it simply, if your function, or if your relation rather, passes this vertical line test, then it's going to be a function. And you pass the vertical line test by drawing a vertical line anywhere in your graph. And if it cuts it only one time, it's okay, it's a function. But if you draw a vertical line here, for example, it's going to cut through your circle twice. That means it's not a function. Okay, so is this really useful knowledge? So-so. not in particular. It doesn't help you calculate anything. But you do have to understand the difference between a relation and a function. And in grade 11, you're going to be learning quite a few different functions compared to grade 9 and grade 10. Usually in grade 9 and grade 10, you just learn about the linear and the quadratic. In grade 11, you have to learn about 5 more. So the jump between grade 10 to grade 11 is usually the biggest. And then grade 11 to grade 12 is not that big. It's almost the same thing. Now, the other term that we want to kind of introduce to students in grade 11 is something called the domain and range. Again, you most likely have been introduced to this term already.
Yeah, we had a test on it.
Perfect. So the domain is simply all the x values on your graph, okay, all the independent variables. And then the range is all the possible y values, all dependent variables. The easiest way to do domain and range, in my opinion, is to simply just sketch out the graph. And by looking at the graph, you have a solid visual and you can figure out what the domain and range is from that, okay? So, well, we're not gonna do any of these questions. These questions are, I'm just asking you what's a function. You're literally drawing lines to see if it passes, okay? So let's talk a little bit about the domain and range. In grade 11, they will teach you how to write domain and range using something called a set notation. And then in grade 12, they will typically teach you how to do it by something called an interval notation, which is, in my opinion, easier. But for now in grade 11, they do want you to write it as a set notation. So if we were to, for example, take a look at the parabola, which is something that we're all familiar with, because I'm assuming everyone here has finished grade 10 math. If you take a look at the parabola, you can see that the domain is going to be x belongs to all real numbers, such that, oh, there's no restriction for this, sorry. The range is going to be y belongs to all real numbers, such that y has to be greater than or equal to 0. And again, you could see this visually from the graph, because if you imagine this graph extending forever and ever and ever, in the left-right direction, the x will eventually reach negative infinity and positive infinity. So in other words, x can range anything, any number between negative infinity to positive infinity. So there's no restrictions for the x. So we simply just says x can belong to all real numbers, can be everything. It could be a negative number, it could be a negative decimal number, it could be a positive number, doesn't matter. Now for the range, we also specify that y belongs to all the real numbers to include all the decimals. But in this particular case, if you look at the graph, my smallest possible y value is 0. I have no y values less than 0 for this problem. Okay, so that means if this problem was to be extended forever and ever and ever, you can notice that y can eventually reach positive infinity, but the smallest possible y value is going to be 0. So in this particular case, we simply state the restriction as y must be greater than or equal to 0. Okay, and as we do grade 11 math, you'll be asked to give the domain and range for a wide variety of functions. That's why it's important for us to be able to visualize the functions as a graph. And once we visualize it as a graph, the rest becomes a lot more straightforward. Okay, so just remember, if possible, we should always have a visual for all of these problems. Okay, and then that'll make our life a lot simpler. All right. Next thing that we have to learn is something called function notation. Have you guys used function notation already in your class? You might have, right, Anthony?
I don't think so.
Don't think so? Well, you know how typically when we're talking about an equation, we like to say y is equal to 2x plus 1, for example, or like y equals to 2x squared plus 1. Okay, so in this particular case, instead of saying y, they simply want you to write function at x equals to 2x squared plus 1. Okay, so function at x basically means what is the y value? What is y when x equals to something? Okay, so if they said what is function at 2, this simply means what is y when x is 2. Okay, so what's the main point of function notation? It's kind of just so that they don't have to write it all out in a complete sentence. Okay, so you know how before, back in grade 10, when you were doing the questions for a parabola, and then they might write, what is the height of the ball when t equals 3 seconds, for example. Okay, so they might, a long time ago, they might write that as an entire sentence. They might write, like, what is the height of the ball when t equals to 3 seconds? Okay, and now, instead of having to write that whole sentence, they will simply just write what is h at 3. Okay, so suppose that my equation was h at t is equal to negative t squared plus 2t plus 5 or something like that. Okay, now they're saying what is, instead of saying what is the height of the ball when t equals 3, they'll just say h at 3 equals to what? And then that's your q. Let's substitute 3 into the t, because remember h at t is equal to this equation. So h at 3 must be, wherever I see t, I have to replace it with a 3. Okay, and then we can solve for this. So it's negative 9 plus 6 plus 5, so the answer is 2. So it turns out at 3 seconds, my height of the ball is 2 meters in the air. Okay, so the main advantage of function notation is that it allows us to kind of say things a little bit faster. Okay, so instead of saying what is the y when x equals 3, just say function at 3. Okay, the other advantage of writing function notation is that it allows us to talk about the transformations a lot easier. Because in grade 10, you were introduced to the quadratic, and you should have talked about transformations already with your teachers. So for example, we have y is equal to 2, x squared plus 3. You probably remember this 2 as a vertical stretch by a factor of 2. And you probably remember this 3 as a vertical translation of 3 units up. Okay, it's a translation for you. Okay, so, but it turns out, but if you think about it, the equation for a line, y equals 2x plus 3, also has the exact same transformations, right? This is also a vertical stretch by a factor of 2 and a translation 3 up. So by by using functional notation, we can have a nice general way of talking about all the transformations. So it turns out this, we can also reword it as 2 function at x plus 3. So basically, it doesn't matter what your function is. Your function could be a line, it could be a parabola, it could be a radical function, okay, it could be something new that you're going to be learning. It doesn't matter. It turns out, regardless of what the function is, the number in front of your function is always going to be a vertical stretch or compression. And the number all the way at the end of your function is always going to be your vertical translation. Okay, we'll talk a little bit more about the transformations later on, but for now, I just want you to kind of understand the advantages of doing function notation. Why are we even doing it? Okay, but to be honest, mostly it's just for convenience. It's a very simple way for us to know what we're looking for. Okay, so for example, in the question number 2, it says the graphs of y equals f at x and y equals g at x are shown. So this is the graph of f at x and this is the graph of g at x. If the question wants you to find f at 1, it's really straightforward. You just need to look at when x equals to 1 and find the y coordinate. So y coordinate is 2. So this equals 2. So remember, the function at 1 is basically, all this is saying is what is the y coordinate when x equals to 1. The y coordinate is 2. Okay, same thing with b. It's asking what is the y coordinate when x equals -2. So if you look at the graph for g at x, when x is -2, y is 4. So yes, answer is 4. Okay, for c, what is function at 4? Well, function at 4 is -1 minus g at -2. Well, g at -2 is 4. That means this answer is negative. Okay, really straightforward. The function notation is basically substitution when we're dealing with these type of numbers. So it's really, really straightforward. I don't, usually students don't have too much trouble with this if you're just simplifying it really, really straightforwardly. But sometimes they get confused when they're asked to evaluate something like this. But you just have to remember, if h at x is equal to 2x minus 5, then h at 3c minus 1 is obviously 2 times 3c minus 1 minus 5. You just replace whatever is within your brackets with whatever is your variable. So instead of writing x, I'm going to write 3c minus 1. So my final answer is 6c minus 2 minus 5, which is 6c minus 7. And that's all. Okay, it's really straightforward. Function notation is just another way for us to say y, the y coordinate. Okay, but it's a little bit faster, more convenient. All right. So this is the first part where it's actually going to go into something new and actually somewhat kind of important. Okay, the previous 2 parts is just introduction, some very basic characteristics. But this one is talking about different properties of parent functions. A parent function is a function that has no transformation. So for example, if you're talking about a straight line, the parent function is the line y equals to x. Okay, it's this green line over here. It has no transformation. It hasn't been stretched. It hasn't been moved. It's simply just y equals to x. Okay, your quadratic function, your parent function is y is equal to x squared. Okay, again, there's been no stretches or compressions. It hasn't been moved up or down or left or right. Okay, very, very straightforward. Your family members are basically all your transform functions. So it's going to be the ones that have been stretched or compressed, shifted up or down. Okay. Now you should already remember linear functions and quadratic functions from your grade 9, grade 10 year. But in grade 11, you are going to learn about at least, like, I would say 5 new functions. Okay, they're as follows. You have the radical function, or they call it the square root function. You have the reciprocal function. And I think sorry, Zoom crashed on me. Okay, so you're gonna learn 3 more functions: the radical function, the reciprocal function, and the absolute value function right here. Okay. Now, have you already seen these graphs by any chance, Anthony? Do you know what any of these look like?
No.
No? Okay. So let's talk a little bit about the different shapes for them. And then we'll discuss a little bit about their characteristics and domain and range. Okay, let's start off with the square root function. Now, I would normally do it on Desmos, but because we're recording, I don't want to keep switching between the screens. So we'll just draw one. Okay, so let's suppose we're dealing with y is equal to square root x. And let's suppose I don't know what this graph looks like. Well, it turns out it's not really that big of a deal. All you have to do is just make a table of values, right? So when x is equal to 0, y is equal to 0, because square root is 0, 0. When x is 1, y is 1. When x is 4, y is 2. And when x is 9, y is 3. Again, I'm just substituting these x values into my equation, and I'm getting the y values. So that means all I have to do is plot these points. So it turns out I plot 0, 0, 1, 1, then 4, 2, and then 3, and 9, 9, 3, sorry. And I kind of end up with this type of a rainbow shape. Okay, so this is the general shape for my radical function. Okay, and then if we take a look at some of the characteristics of this function, you can see that the domain is x belongs to all real numbers, such that x has to be greater than or equal to 0. And then the range is y belongs to all real numbers, such that y is greater than or equal to 0. Okay. So this is the basic parent function for y equals to square root x. And you can still apply all the exact same transformations that you learned from before. So if, for example, the teacher ever asked you to sketch y is equal to 2 square root x, you should know that this 2 represents a vertical stretch by a factor of 2. And that means all my y coordinates are going to be doubled. So I'm going to just make the same shape graph, but I'm going to make the y coordinates much higher. So instead of it going through 1, 1, it's going to go through 1, 2, then 4, 4, then 9, 6 instead. All my y coordinates will be doubled. Okay. So I should expect y equals to 2 root x to look something like this. This is known as the radical function or square root function. Okay, let's take a look at what this reciprocal function looks like. This one's a little bit harder. But this is the basic shape of the graph. You're going to end up with 2 lines, one in quadrant 1 and the other one in quadrant 3. And they're basically going to kind of look like a sideways parabola or a hyperbola. Okay. And there's something quite special about the reciprocal function that we have to introduce. And we're going to be learning about a new term known as the asymptote. And you may or may not have heard about this term before, but essentially the asymptote is kind of like a force field. Okay, it's like an invisible line on your graph that your graph cannot pass through. So in this particular case, you can see that for this function to come up with a real answer, x cannot equal to 0. Because if x was 0, we will end up with 1 over 0, which is undefined, right? So that doesn't make sense. So since x cannot equal 0, we create something called a vertical asymptote. So remember, x equals 0 is a vertical line, right? Which is basically at the y-axis. So there's a vertical asymptote that's created on this equation at the line x equals 0. So the restrictions is x cannot equal 0. Now, what about this horizontal line that I've drawn? Because there's also a horizontal asymptote. Well, it turns out for this, y also cannot equal 0. And the reasoning behind that is because 1 divided by any number will never equal 0. Okay? Even if x was equal to 1,000,000, okay, 1 divided by 1,000,000 is a really small number, but it's still not 0. So 1 divided by any number will never equal 0. So therefore, we end up with a horizontal asymptote at the line y equals 0. So once again, to recap, the asymptote is basically an invisible line that your graph is going to come very, very close to, but it will not actually be able to cross it. Okay, but it's going to come very, very close, but it won't actually be able to cross. So it's kind of like the first view. Now, once again, if you don't remember what this graph looks like, all you have to do is just think about the table of values, right? It's still the same idea. When x is equal to 1, y is 1 over 1, which is 1. When x is 10, for example, well, then y is 1 over 10, so that's 0.1. So that means you have a point at 1, 1. And when x is 10, y is going to be super, super small. And when x is really small, like when x is 0.1, y is 10. So that means when x is really small, y is really big. So if you connect the dots, you end up with this type of shape. And you do the same thing with the negative side. And you will remember what your reciprocal function looks like. Then, I mean, ultimately, the easiest way is to just memorize the parent functions. So just memorize this is the shape of the parent function, then you don't have to worry about the rest. All right, the last one that we have to learn about is the absolute value function. Before we draw the function, you have to first learn what is an absolute value. The absolute value is essentially the magnitude of your number. So it's how far away from 0 your number is. So for example, the absolute value of -2 is simply just 2. The absolute value of -3 is simply just 3. Another way of thinking about absolute value is it's just always the positive version of your number. Okay, so when we're looking at the graph y is equal to the absolute value of x, it looks very, very close to your graph y is equal to x. Oops, not a very good drawing. So it looks very close to the line y equals to x. But instead of this negative portion, we're not going to be allowed to have this negative portion. It's going to be reflected upwards to be positive. Okay, so the absolute value function is going to have the point 0, 0, then 1, 1, then 2, 2. And on the other side, it's going to have -1 and 1, and -2 and 2. Okay, so it creates this type of V shape on your graph. This is the parent function. And again, if you have transformations from it, for example, if your teacher asks you to draw y is equal to 2 absolute value of x, okay, this one's the absolute value of x, then you should know that all you have to do is vertically stretch it by a factor of 2. So my graph will look like this. So all my y coordinates will be doubled. So it's going to pass through 1, 2, and 2. Oh, sorry, why does that say 2, 1? It should be 2, 2. And it'll pass through 2, 4. So this is the base. Oh, they have the graphs over here. So you can see over here the parent functions look like this. Radical function looks kind of like a mirror, looks kind of like a rainbow. And we should write the domain and range. So the domain is x belongs to all real numbers such that x is greater than or equal to 0. Range is y belongs to all real numbers such that y is greater than or equal to 0. For the reciprocal function, the domain is x belongs to all real numbers such that x cannot equal to 0. And then the range is y belongs to all real numbers such that y cannot equal to 0. For the absolute value function, there's no restrictions for the domain. X can simply be all real numbers. But for the range, y can belong to all real numbers such that y must be greater than or equal to 0. And again, the easiest way of doing this is to just visually look at your graph. Okay, if you look at your graph, you will have a very good idea of what the domain and range should look like. Okay, does that make sense so far, Anthony?
Yep.
Yeah, okay. So determining domain and range of a function we kind of already talked about. My recommendation is to not do it algebraically, but rather to do it graphically. Okay, if you think about what the graph looks like, then figuring out the domain and range will come very, very naturally. Okay, so let's take a look at some examples. We wanted to figure out the domain and range for this one. This we already know is a parabola written in vertex form. So if we wanted to just do a quick sketch, this is going to have my vertex at -1 and +6, and it opens downwards because of the negative coefficient. So that means we can see the domain is going to be x belongs to all real numbers. And the range is going to be y belongs to all real numbers such that y is less than or equal to 6. Because my vertex is at -1, 6 and opens downwards, right? That means y can only be less than or equal to 6. Okay, so my recommendation is to think about the graph. Once you have the graph, the rest will come very, very easily. And now you might not know what this graph looks like yet, but you will by the end of the unit. Okay. In order to sketch that graph, you have to learn one more transformation, which is the horizontal transformations. Those are typically not taught in grade 10, so they will only be introduced in grade 11. Okay, having talked about a lot of variety of different functions, we can now talk about something known as the inverse function. Okay, so not to be confused with the reciprocal function, because the reciprocal function that we talked about before is y is equal to 1 over x. Sometimes kids get these terms confused, so they're not the same thing, so just be careful. The inverse function is the function after all its x and all its points have their x and y coordinates reversed. Okay, so all the x and y coordinates will be flipped. So if we had a parabola, for example, okay, where this point is 0, 0, 1, 1, 1, and 2, 4. Okay. If we flip all the x and y coordinates, then we still get 0, 0. We still get 1, 1. Then we get a point 4, 2 instead. We're going to go 1 and -1. It's going to be down here. And then lastly, we have 4 and -2. Now we click connect the dots. We will have our inverse function. And another way of describing the inverse function is that it is, because all the x and y coordinates have been reversed, it is simply a reflection in the y equals the x line. So if you draw the line y equals x. Okay, and maybe this is not the world's greatest reflection. Maybe something like that would be a little bit better. But the two graphs are supposed to be a mirror image of each other once you reflect it in the y equals x line. Okay, so this is another way of thinking about the inverse function. Now, there's a few key things that you should remember about the inverse function and the parent function. The inverse function, because they have had all the x and y coordinates reversed, so to speak, that means the domain and range will be reversed as well. So for example, if we're talking about the domain and range of this parent function, we have the domain is x belongs to all real numbers. And the range is y belongs to all real numbers, such that y must be greater than or equal to 0. The domain of my inverse function is going to be x belongs to all real numbers, such that x has to be greater than or equal to 0. And then for the range, it's simply y belongs to all real numbers. So you can see this domain became the range, and this range became my domain of my inverse function. Does that idea make sense, Anthony?
Mm-hmm.
Yeah, good. Perfect. Okay, so what if we don't want to plot all the graph out and we don't want to reverse all the x and y coordinates? It's a lot of work, right? Is it possible for us to determine the equation of the inverse function algebraically? Well, the answer is yes. Okay, so suppose we are given a function like this, function at x is equal to 5x plus 8. Most textbooks will teach it by simply writing this as y is equal to 5x plus 8. Then your next step is to switch the x and y variables because all the x and y's have been flipped according to our definition. So that means x equals to 5y plus 8. And now you should just re-isolate for y. So you get x minus 8 over 5 is equal to y. And instead of writing y, now you simply write function inverse at x. So this is the equation of your inverse function. Now, do bear in mind that the inverse of a function is not necessarily a function. Just like our parabola example, when we did the inverse function, it became kind of like a sideways parabola. And that actually doesn't pass the vertical line test. So therefore, the inverse function of a parabola is technically not a function. Now let's just practice getting the inverse. Okay, so let's do this one. We have 2y minus 10 equals to 5x. Again, the easiest way is probably to just write 2y minus 10 divided by 5 is equal to x. Then just switch the x and y variables. So you get 2x minus 10 over 5 is equal to y. That means 2x minus 10 over 5 is equal to function inverse at x. So all you have to do is just switch the x and y variables and then re-isolate for y. Okay, that's the easiest way that you can do these questions. Okay, so the next part explores something that you're a little bit familiar with at the grade 10 level, but this is exploring transformations of parent function. So we kind of talked about this very briefly earlier already, but when we're talking about transformations, if we write it in function notation with the f at x, then that means it can apply to everything. It can apply to your parabola, it can apply to your radical function, it could apply to your reciprocal function, it could apply to your absolute value function. It makes no difference which function you're using. They all still obey all the exact same transformations. Okay. So let's take a look at some examples. If we have y is equal to square root x minus 1 plus 2, what transformations are happening here? Okay. So this minus 1 is a bit of a new transformation. Oh, no, wait, no, it's not. No, you guys already learned this back in grade 10, right? So to put it in perspective, this is the equivalent of y is equal to x minus 1 squared plus 2. Okay, and you probably know from your grade 10 that this means 1 to the right. Remember, it's always backwards for the x transformation. So if it says x minus 1, it actually, you have to think plus 1. So it actually move 1 to the right. And this one is 2 up. Okay, so what do we do with this particular graph then? This one's not a parabola, this one's a square root function. Well, it turns out it's the same idea. All you have to do is just draw your square root function. It looks like this. Then you literally just have to pick it up and then move it 1 step to the right and 2 up. So maybe it's going to be around here. And then you draw it again. This is it. This is y is equal to square root x minus 1 plus 2. You just have to follow the transformations. So this point is actually at 1, 2. And then the domain is x belongs to all real numbers such that x has to be greater than or equal to 1. And then the range is y belongs to all real numbers such that y has to be greater than or equal to 2. Okay, so it's easiest if you just think about the graph. As you can see from this graph, my 0, 0 point move 1 right and 2 up, so it's at 1, 2. So therefore, all my x's must be greater than or equal to 1, and y's must now be greater than or equal to 2 in order for me to solve. Okay. Anthony, does this make sense?
Mm-hmm.
Okay, all right. It's the same thing with all of these. You can notice that all 3 of these have the exact same transformations. They all move 1 to the right and 2 up. So all you have to do is just think about what the parent function looks like in order to draw those. Okay, so for the second one, you know the parent function is going to be a V shape. It's an absolute value. So all I have to do is just draw the same thing, except I move 1 right and 2 up. Oops. Okay, like this. Draw 1 right and 2 up. And this is going to be my transform function, this green one. Okay, so it's the exact same transformations as you've seen. There's no difference. It will apply to all the different functions that you've learned about. Now, usually in grade 10, you will talk strictly about the vertical transformations and the horizontal shift. Okay, what I mean by that is in grade 10, usually you've seen this, -2 times x minus 3 squared plus 4. Okay, so this is kind of like the maximum in grade 10. This negative means it's a reflection in the x-axis, so it's been reflected upside down. The 2 represents a vertical stretch by a factor of 2. The -3 represents moving 3 to the right. and the +4 represents 4 up. Okay, so, but you'll notice that back in grade 10, we never talked about the horizontal stretch or compression or the reflection in the y-axis, right? So right now in grade 11, they're going to introduce us to the horizontal stretch or compression as well as the reflection in the y-axis. So that's kind of the new parts that you're going to be learning for transformation. Okay, let's take a look. It says investigating horizontal stretches, compressions, reflections. Now, horizontal stretches and compressions and reflections, they're always written within the function itself. Okay, and what I mean by that is if we have the equation y is equal to x minus 1 squared, if I wanted to give this a vertical compression by a factor of 1/2, I would have to write y is equal to 2 times x minus 1 squared. Okay, so this horizontal transformation and stretch or compression always has to be within your function. So in this particular case, it's a parabola, so I have to put it inside my brackets with the square. Okay. And the second tricky thing to remember for the horizontal transformation is that the horizontal stuff is always backwards. Just like how this -1 actually means 1 right. This times 2 actually means divide by 2. So that's why we say this is a compression by a factor of 1/2. So you can either think of it as dividing by 2, or a lot of times we'll think of it as multiplying by 1/2. So you have to put whatever number is here and put 1 over. That will be your K value. This value will tell you if it's a stretch or compression. So to reiterate, if your K value is a number bigger than 1, it's a compression. If your K value is a number less than 1, then this will be a horizontal stretch, okay, by a factor of 1/2 in this particular case. Oh no, sorry, not by a factor of 1/2, by a factor of 2. It's always 1 over whatever is your K value. Okay, so this is the new part that you're going to be learning in grade 11 about transformations. You have to learn how to write the horizontal transformations. So if we have something like this, y is equal to, let's say, -2 x plus 3 squared minus 4. You need to write these transformations as the following. You have a reflection in the y-axis. Remember, it's inside your function, so it's a horizontal transformation. You have a horizontal compression by a factor of 1/2. Okay. This will move 3 to the left and then 4 down. So these are all the transformations that's happening with this equation that I provided. Okay. Does this make sense, Anthony? Is there anything that you need clarification on?
So it's basically just the opposite of the A value.
Exact. Yeah, kind of. The A value and the, what's the variables you guys use? The C value, like the A and C. So in other words, the number all the way at the front and the number all the way at the end. These ones will tell you your vertical transformations. Everything inside the function will tell you the horizontal transformations. But the horizontal transformations are always backwards. So instead of ×2, it's divide by 2. Instead of +3, it's actually -3. Okay, so that's the tricky part about the transformations. But you get used to it. Just remember that, oh yeah, all the stuff related to the x is backwards. Okay.
So the variable for the horizontal transformation is K?
Yes, you're correct. So the general term that they use, wait, did they give the general term? What's the general form?
So would the variable switch because the
Oh yeah, a
equation
variable will change depending on your teacher, but
Oh, okay.
essentially the variables will look like this. Y is equal to, most teachers use A for the start. Okay, then you have function. So it doesn't matter what function you have. Okay? And then you usually have a K value. This K value represents the horizontal stretch or compression. Then you usually have X minus D plus C. Like, so this is the kind of like the general form that you're going to be writing it. But I've seen teachers use worksheets with all kinds of super weird variables because they're just variables. They're interchangeable. You could technically write it as whatever you want, right? But in most textbooks that I've seen, they will use the A, K, B, and C in order to represent the various transformations. Okay, so just don't forget, A is your vertical transformations. Okay, and if ever you have a negative here, this first negative is going to be a reflection in the x-axis. Because it's a vertical transformation, we're reflecting it up down, so that means it's a reflection of the x-axis. If ever our K is negative, make sure you write this as a reflection in the y-axis. Okay, again, we're trying to reflect it from left to right, so that means it's going to be reflecting along the y-axis. And then the K value is going to be all of our horizontal transformations. So it could be either a stretch or compression, depending on what number it is. The D value is going to be your left and right transformations. And then your C value is going to be your up or down. And that's it. You will have learned every single transformation for grade 11. Okay. Does this make sense, Anthony?
Yep.
Yeah? Okay. Depending on the teacher, they will word it differently. So sometimes teachers don't like to say the word compressed, and they might just tell you to say it as a stretch. Or sometimes teachers don't like to say compression by a factor of 1/2. They just want you to say 2. So just say the transformations however your teacher wants you to say. Okay, but I'm just teaching it based off of the textbook. And generally speaking, when you have 2 as a K value, for example, generally speaking, you should write this as a horizontal compression by a factor of 1/2. And you have to understand what these terminologies actually mean. What does a horizontal compression by a factor of 1/2 mean? It simply means all your x coordinates need to multiply by 1/2. So all your x coordinates is compressed inwards. Same thing if you have a vertical stretch by a factor of 2. It simply means multiply all the y coordinates by 2. So you double all the y coordinates. That's why your resultant graph looks very stretched out vertically. Okay. So this is the basic idea behind the transformations. And if you get good at all of these transformations, then the rest of the unit or rest of the grade 11 math is going to be really a lot simpler because they talk about these transformations for a wide variety of functions. Okay. All right. So let's take a look at some examples over here. So let's zoom in a little bit. So for number 1, it says the red graph has been compressed horizontally by the factor of 1/3 relative to y equals to x squared. So you can see over here, y equals x squared is my green graph. And they're telling me that it's been horizontally compressed by a factor of 1/3. That means the equation of this red line should be y is equal to 3x squared. Because remember, it's been compressed by a factor of 1/3. That means my k value is actually 3. You have to flip it upside down, right? This is all the x transformations. So this red one is y is equal to 3x squared. Okay, another way of writing it is y equals to 9x squared. Both are legitimate. Just depends on how you want to write it. For each function, identify the parent function and describe how the graph of the function can be obtained from the graph of the parent function. Then sketch both graphs on the same set of axes. I don't think this is necessary, but we could talk about the transformations a little bit. We have y is equal to the absolute value of 0.5x. So 0.5 is really 1/2. So the k is 1/2. That means this is a horizontal stretch by a factor of 2. If I was to illustrate that graph, my parent function looks like a v, like this. And we already talked about the coordinates. It's going to pass through 0, 0, 1, 1, 2, 2, etc. My new function, because it's been horizontally stretched by a factor of 2, means all my x's double. So I still go to 0, 0, but then I'm going to go through 2, 1, and then I'm going to go through 4, 2. So my graph actually looks more like this. Okay, so this is how we can use the transformations in order to sketch our graphs. Because we know what transformation is happening, then by using the parent function, we can kind of visualize what the resultant function is going to look like. Okay, so Anthony, what transformations are happening with this one, with C?
Horizontal compression?
It is a horizontal compression by 1/2, but what's the negative sign mean?
It's flipped in the y-axis.
Good job. Okay, so one last thing that we should mention, when you're describing transformations, so for example, if you have y is equal to -2 times 3 times x minus 4 squared plus 5, okay? When you're describing transformations, you should always describe it in order from left to right in order to get full marks, okay? So what you did there, you described this one followed by this one, that one's okay. That one is not that big of a deal. But if you've described the translations, like the fore right, before talking about the vertical stretch and horizontal stretch, the teacher will technically mark that as wrong. Because when you're describing the transformations, you're describing it in the order that you have to apply it. So you have to describe it in the order from left to right to be safe. Okay, I mean, you don't have to, like you could just follow BEDMAS basically. Okay, you have to do the multiplication before the addition subtraction. So in this particular case, when you had the 2 multiplying by each other, it didn't really matter what order. But just to be safe, it's easier for you just to always remember, oh, you just always go from left to right. So you don't have to worry about the order. Okay. If you always do it from left to right, it will always be correct. Hey, why did my screen share pause? Oh. All right, what time is it? 9:28. Okay, that's pretty much time. I don't want to go too far into grade 11 math, just because the first part is kind of silly. We're really just defining what is a function. Okay, it's like baby stuff. First unit, there's really not that much your teacher is going to be expecting from you guys. As long as you understand different transformations and how to sketch the graphs, I would say this is by far the most important thing for grade 11 math in the beginning. Okay, that's gonna be it for tonight, Anthony. Have yourself a great night and enjoy your summer. Hopefully you're gonna go somewhere nice for vacation. And I'll see you around, okay, buddy?
All right, thank
All
you.
right. Yeah, no problem.
Have a good night.
Yeah, you too.